Hi, it's Mrs. P here, and thanks for coming to watch the video. I will be teaching you how to solve systems of equations in order that you can complete your test project over the Thanksgiving holiday break. It's not too difficult. It will seem a little long at first, but if you think back to when you started riding a bicycle, remember how impossible that seemed, and now it's a piece of cake. Same thing with math. The more you do it, the faster and easier it becomes. So don't get frustrated as we walk through this. And if you have any questions, you can always reach out to me via School Loop or my teacher profile face account, which is Jenny Prater. Now, as with any lesson, before we get started, I think it's imperative to make sure that we're on the same page with regards to vocabulary, so that when I speak, you understand what it is I'm saying. So for this lesson, what I really want you to know is that when I'm talking about a system of equations, I'm simply referring to two or more equations that are graphed in the same coordinate plane. That's two or more equations graphed in the same coordinate plane. And just in case the term coordinate plane is one that's a little fuzzy, that is simply what we refer to in class most commonly as a graph. It has our x-axis and our y-axis. It's a coordinate plane. Of course, where the x and y axes meet is called the origin, point 0, 0. So again, a system of equations is just two or more graphs drawn on the same graph. Simple as that. The other important vocabulary word to understand is solution. Now, when we talk about a solution to a system, we're talking specifically about the points at which those equations in the system intersect or meet. The points at which the equations meet. Now, back in our initial quadratics chapter, we talked about solutions, and we learned that solutions of quadratic equations were the same as the x-intercepts. They were the points at which a parabola crossed the x-axis. That's not the case when it comes to a system of equations. A system of equations, instead, is concerned with the points at which the two or more graphs touch one another. In this particular lesson, we're going to be talking about a system comprised of, which means made up of, one quadratic and one linear equation. Again, you'll remember quadratic is degree 2, x to the power of 2, and linear is degree 1. So when it comes to a system made up of a quadratic and a linear equation, the equations could have two solutions, like you see here, 2 points at which the two graphs, the parabola and the line, intersect. They could have one solution, just 1 point at which the parabola and the line intersect, or they could have no solutions, which means that the graphs never touch at all. So again, a system comprised of a quadratic and a linear equation could have two solutions, one solution, or no solutions at all. There are 3 ways to solve such systems. In our solution toolbox, we have the following tools: graphing, elimination, and substitution. 3 tools: graphing, elimination, and substitution. Today we'll take a look at this system made up of one quadratic and one linear equation and solve it in all 3 ways: graphing, elimination, and substitution. Let's start with graphing. When it comes to graphing, you might recall that we always begin with our t-charts. And Mrs. P always recommends that we use the following to populate our x values: -2, -1, 0, 1, and 2. Now, why does Mrs. P recommend those values? A couple of reasons. It shows us what the graph will do both when x is negative and x is positive, as well as when x is 0. And it also keeps the numbers relatively small so that we're not calculating crazy big numbers and we can use our heads. You'll notice here, same x values take place in this t-chart, even though it's a linear versus a quadratic. Now, in order to get the y values, all I need to do is substitute in place of x the x value I see in my t-chart and calculate. I write the answer in the corresponding y spot. So for instance, I take negative 2 squared, which is 4, plus 4 is 8. I take negative 1 squared, which is 1, plus 4 is 5. So on and so forth. Now, if you were coming out with a negative 4 initially when you took negative 2 squared, there's a simple mistake that you can mind in order to correct yourself. That means you're not using the parentheses when you're squaring the negative 2. As we know, a negative times a negative is a positive. Therefore, a negative squared makes a positive as well. I used the same procedure in order to fill in the y values of the t-chart to my linear equation. I substituted each x value for x calculated in order to get y. Take a moment and see if you can come up with the same values in your t-charts. Once my t-chart is done, it's time to go ahead and graph. Now I'm going to do a little close-up here and show you exactly how I graphed. As you can see here, I drew a coordinate plane and I began at my origin. I graphed the first point on my t-chart, which was negative 2, negative 8. Negative 2, negative 8. So I went back 1, 2 spaces and up 8 spaces. Oh, excuse me, negative 2, positive 8. Then I went back to my origin and I graphed negative 1, 5. Back 1, up 5. Back to my origin for the point 0, 4. 0 means I move forward none, but I climb 4. Then it's positive 1, positive 5, and positive 2, positive 8. The plotting of those points gives me the curve of my quadratic equation, which I call a parabola. Now let's graph the linear equation. My first point was negative 2, negative 8. So I start at the origin, go back 2, and down 8. Back 2, down 8. Then it's negative 1, negative 4. 0, 4, positive 1, positive 4, and finally positive 2, positive 8. Connecting the dots for this equation, I see it's a line, as I would expect of any equation of degree 1. Now I step back and I look, where do these two graphs, the parabola and my line, intersect? And I see very clearly that there's one solution at the point 2, 8. One solution, one place where they intersect at the point 2, 8. And that's how you solve a system of equations using graphing.